just gonna wait a little bit and get confirmation that everything is good. Make sure my windows are all in the right spot. Guess I can show my camera. Let's see. My poor computer. Chat. I do. Title is correct. Okay. Not sure how to change. I'm not John Park. Hi. Looks like we're getting folks on YouTube. Let me just pull that up as well. For those of you who don't know, I'm Scott. I'll be... Oh yeah, this does have John Park's thumbnail. I don't know how to change that. I'm not John Park. I just shaved. Awesome. Thank you. All right, we're up on YouTube. Sweet. Good morning, everybody. Well, good morning to Australian folks. All right. Do you want to see my logo? Let's go back to that. This is my, I have my own freelance software company, and it's Chickadee Tech. The Chickadee logo is something I drew, and I put it on all the PCBs that I design. But I added Adafruit in the bottom right as well. So we're 2:01. It seems like you can hear me and you can see me, except now I turned it off. So let's jump right in, and I'll talk about what we're doing today. So for those of you who don't know, please let me know if audio needs to be fixed or anything. Thanks for the cool logo comment. So I'm Scott. I work on CircuitPython for Adafruit. I like to do these deep dives. I don't do them regularly because I'm usually heads down and stuff. But I thought today I had an interesting topic and people would be interested to watch it. So I thought I like to do Friday afternoons because I sometimes find it hard to focus. So doing a stream is kind of like, hey, let's celebrate. It's almost the weekend. Let's do something. So the plan is today, one of my top priorities is going to be working on the ESP32-S2. So I just got this, and it's reflecting. Lamore sent me this. She got 2 of these dev boards, and I'm gonna let the cat out because she tends to make a trouble. It's only once I start talking that she becomes upset, so I'm gonna kick her out right now. Proof of cat. All right, so cat distraction as always. So today I work on CircuitPython. I got a dev board for the ESP32-S2. No, don't kick her out. But she tips over the garbage can. And don't worry, there's a second cat in the background. He's white and he's really hard to see. You can kind of see him at the bottom there. He's laying in his bed. I tweeted a picture of him this morning. It was super cute. But yeah, so don't worry, we have a second cat. He's totally chill. unless he has a seizure because he's epileptic. But, you know, we'll cross that bridge if we get there. Yeah, so 2 cats. They usually hang out in the window here next to me as I work. So today, this is not going to be like those of you who are, this is the first time I've actually streamed on the Adafruit YouTube. I was on Twitch earlier, but YouTube wasn't working last time I did it, so welcome. This is not going to be quite as formal as most of the other streams that you see on here. It's going to be about, I think probably 2 hours is about as long as I can talk. But it's kind of centered around a common theme, a kind of like technical topic that I want to dive into, which is why I call it a deep dive. Feel free to answer questions. It looks like I'm seeing both Periscope comments, Twitch comments, and YouTube comments, which is pretty neat. And so, yeah, so today I'm going in circles. CircuitPython. So for those of you who don't know, CircuitPython is a fork of MicroPython that has been sponsored by Adafruit for about 3 years. 3.5 years I've been working on it. They paid me to get MicroPython working on the SAMD21, which is like our M0 boards. And then we've just grown the project and we've made it into a whole big thing. And as the project grows, we want to add support for different platforms. And we really early on did have support for the ESP32-66, which is a popular Wi-Fi microcontroller from Espressif. And it's really cheap. It does Wi-Fi and people really like it. But as CircuitPython matured, we found that we were teaching people, plug it in, it shows up as a drive and your code's on it. And we simply could not do that with the ESP8266. And we couldn't actually do it. We can't do it also with the ESP32. And the reason that is because the chips themselves, the ESPs, the 8266 and the ESP32, they don't actually have any USB hardware built into the chip itself. What happens is that there is a separate chip on the board that translates between USB serial and like proper serial UART. And that means that you can only really do one type of USB, and that type of USB is your CDC, your serial communication. And that's not what was core to the workflow that we taught people with CircuitPython. We fundamentally couldn't have like that chip show up as a drive. It just didn't, there was no way to do it. So we've been very excited about since Espressif announced this new chip, the ESP32-S2, because it has native USB. Now it's not super fast or anything. It's just full speed USB, which is what almost all of the other boards we support have. Totally usable, but it's such a huge difference between no USB and some USB that we're really, really excited about it. So one of my top priorities, I'm the lead of CircuitPython. I'm not the only person paid to work on it, but I'm one of the core folks. One of our top priorities is to add support for this new ESP32-S2 to CircuitPython. Because we can get the wonder of and the value of Wi-Fi without losing that workflow that we've taught everybody on how to use CircuitPython. Because they know and love it, and we love it too. Having that core consistent workflow of plug it in, it shows up as a drive, it has a file on it, edit the file, save it, and it will reload. That principle of the workflow means that we can have tutorials that just say, this is the process. It works for all the boards that support CircuitPython. And that's incredibly powerful. And we've done 200 plus libraries that have that same sort of principle where almost all of them work across all the CircuitPython boards because we also have a standard API, but we won't talk too much about that today. All right, are there any questions? Thanks, John, for saying it looks great on Twitch. I just turned my camera up, but usually when I'm doing this, it's up in the corner and you'll see that. Okay, so it just went blurry. What we're gonna do today is I want to test. So I want to test the USB side of things. And then depending on how that goes, we might start to talk about how we start adding support for CircuitPython. It's all super early and there's kind of a couple hurdles that we'll talk about when we get there. But let me switch to my screen And we'll talk about, oh, that's the overhead. That has the overhead. We'll do this. Oh, and I changed the size of my video. Let me make that so you can see me. The bottom right. And as always, so the Twitch link is twitch.tv/Adafruit. John Park asks, is the plan to enable both Wi-Fi and BLE on the ESP32-S2 in CircuitPython? And I think the answer is that, as far as I know, the chip does not support BLE, so it will be Wi-Fi only, is my understanding. But I'm just getting into this chip. I'll show you what I got on here. D. Gregoire asks, is the S2 openly shipping now? I don't believe so. And in fact, because New York is, I guess I should talk about Adafruit a little bit. And Unexpected Maker confirms S2 is Wi-Fi only. So yeah, Wi-Fi only. Nordic NRF52840s are great for BLE. So I believe the status of the S2, so Adafruit is based in New York. New York is having a huge impact from COVID-19 right now. Adafruit HQ itself is not manufacturing anything. They have very limited staff. Oh, it's available at Mouser. I didn't know that. So they're doing very limited things there. And Limor got her to, so Espressif sent Limor 2 copies of this dev board, which I will show in just a bit. And because they're all shut down in New York, we actually asked Espressif if they would send me some directly rather than Limor sending me one from New York. And they actually said they were out for the moment. So it's still pretty limited. I did watch Unexpected Maker's video, and he showed that he had 300 modules. So keep an eye on that. But yeah, it's still pretty early. But we're getting ahead of the game on CircuitPython, and you'll see that the USB stuff was just fixed like this morning. So it's all super new. And this will hopefully be a status update on where we're at for everything. Okay, so you can see my screen. Please shout out in the chat if I'm talking about something that my picture is over, because on my screen I can actually see like under what my picture is. Let's start with TinyUSB. So TinyUSB is an open source USB stack written by TAC, who is actually also paid by Adafruit to work on TinyUSB, Arduino, Nordic, and NRF52 stuff. You'll see TAC, his fingerprints on a lot of stuff. So TinyUSB is it kind of started as a hobby project for him. And at some point I got sick of debugging the vendor TinyUSB stacks because when CircuitPython first started, we actually had like Atmel's USB stack, and then another, I guess when we're adding Nordic's stack as well, like I'd found some in Atmel's, some bugs in in Atmel's USB stack, and I was just like, I didn't want to deal with it. Like I wanted to have, what I realized with USB is that the things that make it look like a drive, the things that make it look like a serial port, like all that stuff is standardized. There's no reason for it to be different for every vendor. And TAC had done this project called TinyUSB, where he started prototyping that and playing around with it, but I don't think many people used it at that point. But I was just like, look, we've got to factor this out. We've got to use the one thing. So a year or two ago, I think it was a couple of months, actually, it turned out to be. But I took those couple of months and basically tied CircuitPython's core workflow, the code for CircuitPython, I tied it pretty closely to TinyUSB so that as TinyUSB adds support for things, we could quickly ramp up to the point of having the core CircuitPython workflow working on anything that TinyUSB supported. So I've been watching this stuff really closely, and in fact, Espressif is actually using TinyUSB in their ESP IDF as well. So we're kind of all heads down on this one USB stack, which is great, and it's the USB stack that CircuitPython is tied to as well. So there's this PR. I can drop it in the chat, and I assume it goes everywhere, which is pretty cool. I've got this yeah. I'm using Restream.io, which is what Adafruit uses, and I think it drops everything I put in here in all the different chats, which is cool. So if you want to follow along, I just posted the pull request there. And you can see some discussion. I want to just, as I did on the blog post, thank you to these 4 folks along with TAC. So Pygru and CR1901, they're both really frequent contributors to TinyUSB. So thanks to them. And then SpriteTM and IGRR are both at Espressive. So thanks to those folks for chiming in and helping us sort out some issues with it. But the point is that it was merged this morning. I was going to do the stream anyway to test it and see how well it worked. But it turns out that they seem to have fixed the bugs that they were having. So I'm excited to see if it works. So I did do a little bit of rework. Let me pull up the terminal. Oh man, it's getting hot in here. I closed the door so it would be quieter, and I shut the window, but okay, let's close some of this. I got random terminal tabs open, but I want to start with TinyUSB. So is that big enough? Might be a little small. Let's see if Command Plus does anything. Look at that, it does. That's a bit bigger. So I'm in TinyUSB, and I actually checked out the pull request, but since it did happen, yeah, the merge did happen. They fixed the bugs and they merged it just I don't know, like 5 hours ago, right around when I did the blog post about 4 or 5 hours ago. So instead, what I'm going to do is I'm going to fetch upstream. So what do I call it? I tend to like naming my remotes after the username on GitHub, but that doesn't, I clearly don't always do that. So let's fetch origin. And we can see that things have been updated. Yeah, Unexpected Maker says wicked that they fixed the USB issues. And then let's check out origin master. So I was on the pull request branch, but they fixed it and they merged it. So let's actually just do master. And let's just name this should work. I don't know, master. It could be master too, although I probably have a master. I don't care what my master branch is. I think that's something that hangs people up for Git, is like master is really not special. It's just another name. It's a convention. Okay, so I have that. And the other thing, I was following the instructions in this pull request. And they are at the top. So my goal is, should work, yeah. I like to say things should work. Like, I always have bugs in my code, so that's the way it goes. Yeah. I like to be specific. Yeah, I tried to do that. Yeah, so Sedacious in Twitch is saying you can do git clone -o in the remote name and then the repo to set the default repo. It also sets its name to not origin, which is nice. I tried to do that, but I guess I didn't when I first cloned TinyUSB. Let's show what I have on the overhead as the other background. So here's my overhead. I have it pointed to the USB hub here because I don't have that much room. So let's open this. It says the ESP32-S2 Sala IR. It's upside down. I can switch it with this button. Wow, it's right side up now. And then you can see it's actually like straight up written for Lamore. She sent it here. And let's just do it like unboxing style. I will lock. I'm going to lock the focus there, even though I'm going to move it closer. Let's just open it. If you've watched like Unexpected Makers videos and stuff, you've probably seen this hardware already. Although Unexpected Maker has his own hardware that looks really neat. I don't think we've laid out any Adafruit stuff yet, so we're just using this dev board. Let's see what Gregoire asks. Gregoire asks, anyone know the difference between the 1R and the 1M versions of the S2? That's a great question. I do not know that, but maybe by me reading it off, somebody can answer. Let me see in the Discord chat too. Awesome. And TwitchBot posted as well. Yeah, I don't actually know the difference, so I can't tell you, but maybe Unexpected Maker does. And then the thing here is what I was talking about. The chat's distracting me. So on this board, it might be a little blurry, but that's okay. There is this conversion chip that I was talking about is common on the other ESPs, the ESP32 and the 8266. So this dev board is actually also doing that UART or USB to UART conversion. But they did break out the USB pins. So what I have here to test the native USB is an AM data cable, which has just pin headers on one end. So we'll have to triple check our wiring on that when we start to test it. But I think what we'll want to do first is just load through the regular USB, and then we'll try through the side or whatever. We'll see if we can connect. So this is a fancy, I used to work at Google. This is a fancy USB cable I got that has this neat button to click on and off. So when it's green, the data lines aren't connected. And if it's orange, the data lines are. It's like a caution. Make sure you know what you're plugging into. And then I showed this cable to Lamore, and she actually stocks on Adafruit a similar cable. Here, it's just like a pigtail, nice and short, but it's got a switch that says charger and data. So you can just switch it between, like turning the data lines off and on. It's super handy if you ever are doing USB debugging. What I was finding before I got this set up is you would, as you're like working on your USB code, you can get it into a hung state. And like, if you're like I like to listen to music while I'm programming, and I'd find the music actually stutter and stop as like I'm stalling the USB bus because I'm not doing the right thing. So these cables are a lifesaver, so that you can quickly like disconnect the misbehaving device, your own device, from the USB bus. And yeah, usually it's okay. We had some bugs in CircuitPython where we would actually properly crash my Mac, which was really bad. Like I'd get back to my desk and it'd be starting up again because like we weren't doing like the sleep suspend states correctly, but we are now. We shouldn't be a problem anymore. But yeah, it's amazing how USB can really mess you up. Okay, so I've got this cool cable. I've got this, and let's just plug it in and see what happens. I don't even know. Before I switch back to my terminal, we get a red light. I don't know what that means. We could see if I switch to this and I try to adjust that. This cable doesn't want to lay the way that you'd actually be able to see everything. Oh, and of course, my video is gigantic again. Let me just do that. Oh, I had it all set up so nicely, but that's okay. I'll just stick those there. Okay, now you can see me again. I know you just want to see me with my like way too long hair. Okay, let's follow these instructions. So I think I did install the toolchain, but I believe I have to set the environment variables again. So here I am. I'm still in TinyUSB. I should be on a different branch. Let's see what this says. Oh, you know what? This is TinyUSB and CircuitPython. I have two copies of TinyUSB. This copy, the one that I was testing it on, is not on master. And the font size changed just in one window, which is weird. Okay, so let's see what I named my remotes here. And see, I did name it after TAC. So let's just do the same thing I did before. So GoJimmyPie answers the question about I versus R. R has PSRAM, M does not. Thanks, GoJimmyPie. Toddbot says, I use a USB hub with switches per port to accomplish a similar task for taking devices on and off the bus quickly. And Vanessa Kitty says hi. So hi, Vanessa Kitty. Okay. What do I have here? Some secret stuff? I don't think so. I don't think I need that though. Let's just get rid of that. And maybe I have ESP. Yeah, it looks like I've got ESP stuff in my command. So let's try building. I think is how you do it. No such file or directory. I'm very new to this. There we go. It's in my path. Hi, Alvaro from Costa Rica. No problem. I'm glad you're here. I tend to talk a while, so you've got plenty of time to show up late. All right, so what we're working on for those of you who just joined, I work on CircuitPython. Today I'm playing around with the ESP32-S2, and I'm just doing the very bare bones. My goal is to get the TinyUSB CDC and mass storage example running on the S2. And if I manage to do that, we'll go from there. But it always takes longer than you think. So let's see. This looks like it worked. And we should be able to flash. So I wonder what happens if we just type flash. Building, building, building. And it was unhappy. Resource busy. Okay, so let's see. My keyboard and another USB serial. So Unexpected Maker says, all will rovers have PSRAM, all will rooms don't, and the designator is u.lf. For those of you who know ESP better than I do. Okay, so the question is whether this device is the ESP. And there is a way to get into boot mode that I'm probably not following. But we can also just, I'm going to unplug it and just see if it disappears. Like as a validation, because who knows, I might have like a CircuitPython. Oh yeah, if I remember right, and you can, let me make sure you can see what I'm doing. I'm like trying to watch the chat end. So here's the board. I think what I do is if I hit boot, if I hold boot and plug it in, or if I plug it in, hold boot and hit reset, maybe that'll do it. What's the magic combination? Let's see if that works. Hold reset, press boot. All right, let's see if that worked. This is perfect. Build, 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 and it didn't work. Why is it saying resource busy? That's weird. Let me try it again. Ian Pawa asks, how long till ESP32-S2 boards start hitting the market? I think Unexpected Maker is the person to ask because they're probably going to have it first. I don't think Adafruit has any designs done. I know it's something Lamore can whip out pretty quickly, but because of the pandemic, it's kind of up in the air as to when we get going. So if I hold reset, press boot, how do I know? How do I know I'm in boot mode? Still couldn't work. Do the lights change? Let's see, there's a pretty good getting started doc. Let's see if I have it open in one of these tabs. What is this? CMake, datasheet for the modules, technical reference, how to use the build system. I don't have Mu open. No, I don't usually have. You should see. Yeah, I have like a combined chat that I'm seeing, so I'm responding to all of it. Okay, so Theo says, open the serial port and reset the board while having boot pressed. You should see the bootloader message. Okay, I'll try that. Not tiny logic friend. I hate that it doesn't autocomplete. Is there a particular baud rate that I need? See, I couldn't find it either. Let's try. I was thinking about that. What if I do this stream? Okay, Unexpected Maker says you don't need to press anything on the Sala. Okay, well, I'm not press. Oh, well, let me even see again. I was thinking like this is prototype hardware, so it's totally possible that I got one that just doesn't work. That would be just my luck, wouldn't it? But you saw me take it out of the bag. You know it's fresh. Okay, so I'm going to unplug it and not press any of the buttons. And I'm going to plug it in, and then I'm going to switch. I got to make it so I can read the chat and watch the video. Ah, okay, so Unexpected Maker says I'm looking for, oh, wait, it says sorry. The TTY slab to UART. But I'm not seeing that, and I might not have the driver for it. Resource busy. That's so weird. Oh, you know what could be You know what it could be? It could be if I have a driver for it, or if I have an old driver that's snagging it but not finishing. So let's go. Is it a Silicon Labs chip? It is. It's a CP2102. So let's install some drivers. And by the way, this is why native USB is way better. But I'm a little biased. If you haven't used the UF2 bootloader, you just double tap reset and it shows up as a drive. It's very simple. Okay. We don't want Windows 10 because I'm on a Mac. 5.24. Let's take a look at the revision history. Ooh, February 25th, 2020. That's pretty recent. Let's download it. I downloaded it in October. But this will update it, which will be good. That's the one, 5.24. Okay, Toddbot says, yes, UF2 is amazing. Carlos Diaz says, tell IDF which port to use. And Rogan Dawes points out LSOF will tell you what is holding the port open. I love community debugging. It's awesome. And yeah, Unexpected Maker says you will have to install the Scilab driver. Okay. Double click this. Yes, open it anyway. I read the license, I swear. And you can't see the password. All right, tell me when I'm back. Can you see me? Apparently OBS doesn't like it when you install stuff. Okay, Ian Pawa says I'm back. Perfect. That was good. Oh, and here's the crash dialog for OBS. Oops. Okay, so you know it wasn't me. It was a seg fault. Invalid address. Yeah, well. Oh no. It's the Silicon Labs driver needs me to restart. Let's see. Can I just close it? Let's see if it works anyway. Otherwise, I might have to take a brief pause. It's still running. I closed it, but it's still running. Oh no. Let me just quit it. Let's see what we got here. We don't have anything. Okay. Yeah, Toddbot says you should be able to force quit the installer. That is true. Unfortunately, well, let me unplug and plug it back in and let's see. Bruce says, well, different channel, same problems. Yeah. Professor Sparkle says it wouldn't load a new driver on an already mounted device. Right. So I'm going to unplug it and plug it back in and we'll just see if it works. And I should check it doesn't work. Okay. Hi. This is the chat monitor. I did not anticipate this. I would have installed the driver if I had realized that I would need to. Again, I'm spoiled by having USB devices that don't use drivers. All right. Do we have any ideas on how I could keep streaming while I restart? I don't think there are any. It's the same computer. Huh, yeah. Yep. Well, so the good news is that once we load it, we should be able to have native USB and we don't have to deal with this anymore. So, okay, the only thing I can do is I can restart. So, oh, if it doesn't have the USB prefix, let's try that. Let's just do TTY star. Nope, still not seeing it. It's got Bluetooth in my headset, but it doesn't have anything else. All right, Rogan says just do it. So I will. Everybody, like, take 5 minutes. And Bruce also says that they'll restart their Windows laptop in support of me restarting. So, okay, I'll be back. I'm going to take a break, open the window, and restart my laptop. And I will be streaming shortly after I have the new Scilab drivers installed. things are popping up. How's it looking? Twitch says it's sending data. Ah, perfect. Yanni says it looks good. Ian says it's live on YouTube. Oh, and a whole lot of people. Awesome. Rogan says back. Ian says looking good. Unexpected Maker says we're back in YouTube. Simon says good evening from the Lockdown UK. Hi from Seattle. This is not the start of my stream, but I had to install a driver and it required a restart. So we'll do a recap and then get going. Let me just check my messages. Okay. I do have the windows open here and here, so if there's a bunch of background noise, I'll close them, but I was getting quite hot. All right. So, moment of truth. What we were doing is we were trying to get our initial demo loaded onto the ESP32-S2 development board. The goal in the long term is to get CircuitPython running on it. That's already clearly not going to happen today, but we'll see how far we can get with the TinyUSB demos, and maybe we'll end by talking about the things that are next steps. So yeah, shout out if it's not running on the streams. I think it should be. We had folks on Periscope, which is Twitter, Twitch, YouTube. Looks like Facebook's up. Facebook, YouTube, Twitch, LinkedIn, Mixer, Periscope seem to be all online thanks to Restream. I know. NYC Kid says, after all this lockdown, I could use a weekend in your wallpaper. I know, Catalina, right? Like, it's the default Mac background, but it's beautiful. And it's been beautiful here in Seattle, so I actually have been going for runs. But besides that, just hanging out at home, hacking on all sorts of different stuff. Okay, so here we have the ESP32-S2. We're super excited about this chip because it's got native USB, and we've just pretty clearly demonstrated why native USB is better than the bridge chip that's on there now. For those of you who don't realize, I had to restart my computer to install the Scilabs drivers. So let's see if they worked. Can you get a merged restream chat window up in OBS so we can see everyone else's chat? I don't know. It's a browser window. I don't know how to do that. It's mostly YouTube, so if you're on YouTube, you're seeing everything. And it doesn't merge Discord, which is actually my preference. But Drew and Mr. Certainly are watching on Twitch, and they say it's working. So I'll try to recap basically everything I see on the chat as well. It's distracting me, but you know, it's Friday afternoon. It's fine. Okay, so let me log into my SSH off the screen, which is really just copying and pasting. But I definitely do not want to paste it here. So I'm going to type some random stuff and copy it back just so that you can't see it. And double check. I actually did, in one of my earlier streams, I did have a key that I showed up. Luckily, with keys, you could usually revoke them, which I promptly did. Okay, so we have a new terminal. We were in, I put it in repos, TinyUSB. We were in examples, device, CDC, MSC. Free RTOS. That's probably not going to work, but let's just see if our USB connection is. So you can see that too. Take my fancy USB cable and let's just plug it in and see what we get. Because if we can't connect to the bootloader, like I forget who it was, but pointing out that we can just connect over. So let's do that. And we still don't see it. Maybe it's CU. Bummer. All I get is a red light on it, and I don't know what that red light means. Somebody in Periscope's not a fan of the ESP IDF. I haven't gotten that far. Did you do the system's permission thing in macOS? Unexpected Maker says the red light is just a power light. I didn't do a system permissions thing. I can look at my D message. Let me do it off screen to make sure that I'm not a little paranoid. The other thing I could look at is I'm on the latest Mac OS. Yeah, Theo says on the ESP32, not the S2, the bootloader message should be streamed at two different baud rates. Thing is, I'm not even seeing the device at all. So this stream might be turned into fixing getting the Scilab drivers working. I didn't do idf.py set target yet, but I think we're having problems that are earlier than that. Because it should show up as a serial device, and we saw that it was showing up as a serial device, but it wasn't. Now it's not even showing up as that. I can also try doing it directly rather than. Yeah, Professor Sparkles says, I wonder why those even need drivers. I don't know. It might be because I think some of them do GPIO. So Ian asks, what are the other two serial devices? So this one here is my this one here is my keyboard. I have a keyboard IO. KBIO is keyboard IO. Yeah, Unexpected Maker says, I can't remember if or what permission is asked for. It was a while ago when I installed. We can look in the system preferences. I think there's nothing in there that I can't show, right? There's this. Privacy. Maybe I'll just install it again. Or pull up the instructions. Oh, Professor Sparkles says, did the driver install at all, though? The last page sounded like it disrupted installation and was asking for a restart before continuing installation. Okay. Yeah, we can try that. I'm going to move this so you can't see my files. And I can close my Spotify. Maybe it didn't need a restart at all. Let's see. I'm sorry about this. I should have made sure that I had everything installed, but this is programming. This is what happens. It's not like you just magically finish everything immediately. It takes persistence. Okay, so this says currently nothing is installed. So Professor Sparkles is right. He also says, oh, it's great. This is very real. Yeah. So those of you who are under the impression that programming is I'm having great luck today. Okay. Live for the third time. Maybe. All right, chime in the chats if you can hear me and see me. Hello neighbor says, yay. We're all back, baby. Oh yeah, now you can see my screen. Summersoft says a wild slab USB to UART appears. Simon says, welcome back. Thank you, everybody. I found a way to crash OBS reliably. But we're making progress. All right, how are we doing? Do we have the Periscope Twitter people? Sion says, wow, you're confident beaten. The Scilabs chip just knows I'm trying not to use it. That's why it's like hanging on for dear life. Okay, looks like everything's going. Summersoft says the only way out is through. It's very true. All right, do we have any Periscope folks? I really appreciate y'all hanging in there with me. I will. I'm recording this as well, so I'll just smush them all together for folks who are watching this later, and then I can hide the recorded videos. So Theo, it does look like the driver is loaded. So what I didn't show because I was worried it would just crash OBS again is the Silicon Labs driver dialog. I typed in my permissions. That's when OBS crashed, but it like rebuilt the driver database and then it installed OK. So I did, before I brought OBS up, I did try to plug it in, and it looks like it's appearing. The other thing I want to say thank you to Ogre Drew on Discord pointed out that my cable will also disconnect it, so it won't appear. So always remind me as well when the power blips on this cable, it goes back to the green mode where the data lines aren't connected. So yeah, between getting that going and connecting it, it looks like we've got something, which is great. I'm probably not like in the IDF mode anymore because I did do a restart, but let's just, I think we'd have to do a -P. We certainly want the slab one, so it doesn't try to guess the wrong thing. Theo says, okay, great. I missed the beginning of this live. Yeah, I think as long as, yeah, hopefully the recordings are okay, but I shouldn't actually make any promises. Okay, so now we need to get our ESP environment going again, which I just did for the first time yesterday. So we're going to do push D, and then I think it's for away and ESP IDF. If you have not used push D and pop D, it's really handy if you're going between one directory and back to the one. I don't use it actually all that often, but I thought of it now and it makes me look smart. Okay, so we're going to do install and export. And I run fish. Gives me all these nice autocompletes and stuff. And export. That looks right. Oh, what is that? That is not what I want. Oh, I wrote whatever that does. Okay. And export IDF path. And let's source it. Hey, look at that. Now we can do pop D and try our command again. Work. Heyo. We're making progress. Nice. Okay. Maybe I should have done a hello world. Well, we'll see what this does. Oh, I don't need to pass the -p. Well, I'm glad it works with -p. Okay, so I don't know what that does. Let's bring up our trusty. Of course, I lost the window. Actually, I could probably get back that window that had all of the stuff. All of my references. Oh, there's my history. Great, glad you can see that. I don't think so. I watched Sion's video earlier. Okay. So you can see my window. TinyUSB. Pull requests. And it's closed because it was merged. And port ESP32-S2. So if it loaded correctly, I should be able to connect my USB breakout to the pins and get something. So on here, I'll switch to the overhead and you can sanity check my wiring. Okay, so here's the chip. I'm gonna try powering it. So I assume that, actually I don't know the color coding. I assume black is ground. Actually, let me unplug this. Black is ground. Red is 5 volts. And then which white and green are D plus and minus? And I don't know if it's going to reach. It's going to be awfully close. But I don't actually know which one is which. So let's pull up Adafruit. And I'll switch back so you can see it. Ah, here we go. Professor Sparkles has me covered. Says green is plus, white is minus. Green is plus. Okay. So plus goes on 20. So 20 is here. And white is 19, which is 1 in. So double check me. You can see it without being blurry. But it should, 18 is the far right, and then 19 and 20. So white should be 19, green should be 20. And then hopefully I can power it. So ground is black, red is 5 volts. All right, does everybody think that that's correct before I plug it in and maybe just make it go poof? This way I'm not responsible for it. We should see it show up as a drive. Maybe I'll pull up my finder here. Unexpected Maker says yes. As long as power is correct, all good. Yeah, true. Okay, so I'll bring this up and switch to here. So what we should see is we should see a drive show up if it's all working. So I'll plug it in. We have a light, which is good. Oh, look at that. Woohoo! TinyUSB mass storage. Nice. Nice job, Tack and crew. This is TinyUSB's mass storage class demo. If you find bugs, go to the repo and let us know. Okay. Professor Sparkle says, I think some USB PHYs can even deal with the reverse polarity data. Oh. And Unexpected Maker says you'll still need to do the press boot on power up. Why do I need to press boot? I mean, if I want to flash it again, right? But nice. I'm just over an hour into the stream and I got that far. All right. Things are looking up. It only took 2 crashes of OBS and 1 restart to get here. All right, let's see if we can screen to it, which we should be able to do. And I think it's the I didn't lose my magic smoke. It's true. I think it's the 1, 2, 3, 4, 5, 6. With all the restarts, I missed the flashing the board bit. Yeah, it was pretty quick. It actually didn't. It was at the start of this version of the stream. But it looks like it worked. It said hello. And it's echoing back, so I can type and it shows up. All right, so great. We're done. No. CircuitPython just magically works now. Okay, so that's cool. I thought that I knew there would be some trouble. I didn't know what the trouble would be, obviously. So let's recap. We're an hour in. I tend to do these streams for 2 hours. So if you're all hanging in there with me, I'll keep going. What we have is the ESP32-S2, which is a brand new chip from Espressif that is somewhere between their ESP32 and their ESP8266. It's single core. Actually, we could talk about that. We could pull up the data sheet. How fun is that? TinyUSB is an open source USB stack that TAC works on along with some volunteers. TAC is paid by Adafruit to work on it along with other stuff for Adafruit. CircuitPython uses TinyUSB at its core to do all of the USB stuff that it does. That is critical to the way that CircuitPython works by showing the drive and automatically refreshing when you save a file. So this is the first step. The first step is getting TinyUSB support, and then we should pretty quickly, hopefully, get to the point where we'll be able to get a REPL. We'll be able to get a mass storage device showing, so you'll get the drive. That shouldn't be that hard. So let's just talk more about the ESP32-S2, and I can then comment kind of on what that means for CircuitPython. And so yesterday as I was starting to think about this, I kind of like to do this, like preload all this information in my brain and then let it kind of stew and simmer and let my brain work out the decisions I have to make about how I'm going to structure the code, where I'm going to start, what order I'm going to do things in. So let's go that direction. How does that sound? I'll answer questions too. That's a great thing as well. So Professor Sparkles on YouTube says, is there a lot of differences in terms of other peripherals, or can a lot of MicroPython stuff be reused for CircuitPython? And Drew the Ogre says, dev while sleeping is totally a thing. It's totally a thing. I agree. In this case, it's also going to be dev while playing Animal Crossing this weekend. Okay, so the peripherals themselves, the way that we use them doesn't vary that much. The thing that's different is that we actually have a different hardware API than MicroPython does. And the reason for that is because we wanted to come up with an API that would be uniform across all of our ports. So if you go to CircuitPython. Let's talk about this. I like talking about this. CircuitPython.org/read the docs, and you hit core modules. You can see all of the different modules that we have. And one thing that we've chosen to do is that, by and large part, we'll either include a module, well, the module will be there and all of it will be implemented, or not. So, for example, on the NRF 52840, they don't actually have a proper digital to analog converter. So like audio I/O would not be available at all. So if you do in Python import audio I/O, you'll say import error not available. And the reason that, and that's the level of units that we want to be able to do that. And that the reason that's a good approach in Python is that imports almost always happen at the top of a file, and they almost always happen at the start of execution, which means that if you import something that is not available, you'll find out immediately. You won't find an hour later when you try to use it, which definitely can happen in Python. And by doing it at import, it means that you'll find out pretty quickly that you're making an assumption that's wrong. So this is our standard API, and these APIs apply across all of the different ports. And the way that we do that, let's deep dive a little bit here, is in CircuitPython, so github.com/adafruit/CircuitPython, we have a separate directory for all of the layer that translates Python to C. And that's the shared bindings directory. And you can see here that the shared binding subdirectories match up with the listing in the docs. And then you can click into like I2C is one of the first things we would do. So here's bus IO I2C, and we actually include the docs for the Python version of the API in line with the C code. So here are the docs for how it looks from Python, and then here is the C code that actually implements it. And then in the implementation, we have these common HAL underscores. These are C-level APIs that all the ports implement. So when we add I2C support to the ESP32-S2, we'll implement common HAL bus IO I2C construct with those arguments, and then we'll call into the ESP IDF later to make it actually happen. That means that all of this code between Python and C is all shared, and it means it'll be identical, which is awesome. Because identical means that you can build drivers on top of it, and all those drivers work regardless of what platform you're on. So that's the goal. Let's find the ESP doc, and let's talk about some of the things that I'm trying to get in my brain so that they can stew over the weekend. ESP32 datasheet, although that's not specific enough. Although I have it open over here. Hey, look it restarted my window and I didn't realize it. Perfect. So I can close these two. Okay, so let's just peruse the S2 datasheet, and let's talk about, this might not be the only place we can talk about the things that we need to consider. Let me switch. We don't need to see the overhead because I'm not doing that. When OBS crashed, it moved all my windows around. Sure. Okay, so there's kind of three things I'm thinking about is what I would say. Only one of them is really ESP datasheet related. But I guess for those of you who don't know, we can just go over the highlights of it. So the biggest thing it's known for is its Wi-Fi. It's got Wi-Fi. The chip itself, the CPU runs at 240 megahertz at the top end. It's got 320 kilobytes of SRAM, 128 kilobytes of ROM. And it also supports external SPI, QSPI, and OSPI, flash and external RAM chips for memory space. And this is actually quite common in the modules that Espressif produces. They include external flash and external RAM as well. So you actually get quite a lot of flash and quite a lot of RAM. And in fact, if you didn't realize it, the ESP modules, the fact that they included SPI Flash externally was actually the reason that we thought of doing express boards on Feather, which include external SPI Flash. So that's where we got the inspiration for that. Here's the block diagram. Block diagrams can be pretty interesting from time to time. This one is not as interesting as some of the others I've seen. One of the reasons for that is, oh, you know what? I don't have the chat open. So I'm just going to ramble. Wait. Do I not have the chat open at all? I thought I did. Oh, I have it open in the... Okay. I opened it in the tab I moved over. That's why I don't see it. All right. Professor Sparkle says, yeah, that makes a lot more sense, but I don't remember when I don't know when they said that, so great. Glad things make sense. Okay, I can see the chat again. Professor Sparkle says, I love good abstraction. Yeah, hopefully the shared binding stuff makes sense. Okay, close. Reddit, we don't need. Datasheet. Okay, one of the things that's really interesting when I'm usually looking at a diagram, yeah, Professor Sparkle's with respect to the MicroPython versus CircuitPython hardware layer. Yeah. So one thing I look for usually in a diagram like this is how things are connected over memory buses. And this is something that's come more on my radar. The thing that I want to talk about with the datasheet, which is some of the other platforms that we're starting to add support for are the STM32F7 and H7, which they go as fast as 480 megahertz in the CPU. And then the IMX RT series, the 10X series can go up to 600 megahertz. And the challenge is, and the thing that kind of like I'm inheriting from my traditional computer engineering degree, is that memory can't keep up. Right? So the CPU can move really quickly. It can process a lot of instructions, but the memory itself may not be able to actually load the code fast enough to make it worthwhile to be running at that clock speed. That's not so much an issue on the like SAMD21 and maybe even the 51, although the 51's like on that gap. So the SAMD21 is 48 megahertz and the SAMD51 is 120 megahertz. And that's right around the cusp, I think, of like how fast Flash gets. And then after that, you kind of don't benefit anymore. So something that's been true for these ESP chips, even from the ESP32-S2, I believe, is that the cores are quite quick, but the memory isn't necessarily, especially when it's external. So one thing I was looking at when I was reading through this last night is actually the memory buses, their speeds, and the caches that are there as well. So let's just scooch through this data sheet and talk a little bit about memories. So this 320 kilobytes SRAM, that's valuable memory space because that's on board the chip, which means it's much likely to be faster than external PSRAM. So people are like, oh, 4 megabytes PSRAM, that's great, but like it's all slow. Like you can't access it very quickly. And so in CircuitPython, we've started to designate the core VM stuff as critical, and we actually place it closer to the CPU itself so that it can run faster. So I just warped in the datasheet to the CPU and memory section, and we can see a bit more details here about it. It's a 7-stage pipeline, clock frequency up to 240 megahertz. Some interrupt stuff that is kind of interesting. So I guess let me take one step back as well, and that the ESPs here, they're not ARM architecture. So almost all our platforms are ARM of, M0, M4, M7. Those are all ARM architecture, and they have a lot in common with everybody else. Yeah, interesting. So Unexpected Maker says the good news is the S2 has separate cache for flash and PSRAM. Currently, the ESP32 has a shared cache, which is terrible. Yeah. Professor Sparkles asks, how does that work then? Is the PSRAM just mapped to the end of the SRAM address space? Let's take a look. This is a deep dive. That's why I like deep dives. So these are the internal memories. Another thing I've been doing is low power sleep modes. So this SRAM in the RTC and the RTC slow memory stuff is interesting from the perspective of you can turn off much of the chip by like not powering it at all, but you can still have some memory that lasts, which is kind of interesting. And then here, they also tell you like how much external memory space you can actually have. It says up to 1 GB of external flash and RAM can be supported, but there's high-speed caches that can only handle up to 7.5 megabytes or 4 megabytes of read-only memory space. And then we have address mapping structure. It can tell you like these are the memory addresses that you would write to peripherals with. These are the memory addresses that are accessible, are external memory through the memory map unit, which is MMU, and then the cache on top of that, which is kind of interesting. It's also interesting. So for those of you who haven't taken CPU design courses, I think there's at least two, if I remember right, there's kind of two common architectures to CPUs. It's only been like over a decade since I'd studied this, but it's von Neumann and Harvard architecture. And one of the things that distinguishes those two is actually how many memory buses you have coming out of the CPU. And Harvard architecture, if I remember right, has at least two memory buses, one for instructions, which is your assembly code loader, and then one for data, which is like read me a value and put it in a register sorts of operations. And on top of that, what you get, or outside of that, is you get separate caches. So you get an instruction cache and then you get a data cache. And it tells you like how it computes that and like figures stuff out. But the interesting thing to me is the size. I tend to actually want the size to be higher because my goal is to run fast. And CircuitPython is quite a large code base. MicroPython, this is true for them as well. It's a large code base where most of the code you're not going to use, right? So like we were looking at all of the native modules, and the likelihood that you use a lot of like, we can't really guess which of the native modules you're going to use. So we can't automatically put those close to the CPU when you use them. Instead, we have to rely on the cache to do that. So the VM, obviously, you're going to use, and so we'll put that in memory that is not cached, but is also right next to the CPU. And then we'll use the caches for the stuff that we don't necessarily know that you're going to use. Okay, let's scroll down. There was one interesting tidbit that I was looking, that I saw last night. So these are all the different peripherals on the chip, and I would like to think of these as like just something similar to an I2C sensor that you would have on a board. Like they're really, in a lot of ways, disparate and separate from the CPU itself. And so I think it's important to realize that. They're not connected over I2C usually, but they are kind of distinct things. And in fact, I just scrolled by the USB one, but the USB peripheral here is actually just a common one that you can buy. And so it was actually quite quick to get TinyUSB support, because it's also the same peripheral that happens to be in like STM and LP and NXP chips. So we already had support for it. We just had to figure out, one, how that peripheral is hooked up to the CPU, and two, like what configuration settings they had used with it. But once I figured that out, I don't think it was too bad. Not going to talk about this stuff. There's lots of cool things. Pin mappings are always important when doing stuff. But my voice is starting to get tired, and so I should... Got 35 minutes or less, we'll see. But there's two other things I want to talk about. But let me finish up the memory stuff because there was one other interesting tidbit that I saw when I was looking. So the technical reference manual has more information, and it's a lot more detailed. It covers registers and stuff. And I was happy to find this. For Atmel, they like include all this stuff in the data sheet, but for others like the IMX, like they also include it separately. So let's go look at memories a little bit more. An unexpected maker might be able to guess what I'm thinking of. Yeah. So unexpected maker says it's nice that Espressif didn't try to make their own. It's true. So Nordic did. Nordic made their own USB. But I guess that's a Nordic thing to do. They like to make their own peripherals. And yeah, Toddbot, we would like to do USB host eventually. We'll see. TinyUSB actually has limited USB host support. I've never tried it, so I can't vouch to if it works or how well it works, but I think it's in there. Okay. So here's more detail about memory. And here's where they talk about data bus versus instruction bus, which is like how the CPU accesses memory. And how much more they have. DMA is direct memory access, and DMA can be really handy if you say you have like 100 bytes that you need to send over SPI. You don't need the CPU to like shuffle each of those 100 bytes. You can just have something else manage it for you. Okay, there's the memory chart again. Where is the thing that I was thinking of? So the thing that I found interesting, here's more memory address mapping stuff. It is interesting that there's two SRAMs, and this first SRAM is the one that you can configure to be used as the cache. So I'll probably actually use this 32 kilobytes as CPU cache instead of as RAM. And then the 288 kilobytes I'll probably have as like CPU or as like regular RAM. External memory address mapping. And you can see that depending on which address ranges you use, you either get the iCache or the Dcache. So are you storing code or are you storing data for that code? And then here it talks about the CPU cache, things you could do with it, DMA. Yeah, peripheral buses. This is the thing that I thought was pretty interesting. Usually what I've seen is that you'll have, so on SAMD, you'll have 6 circoms, right? And a circom is something that can be I2C, SPI, or UART. They have like enough properties that they make it one thing and you just tell it which mode to be in. But on an ARM chip, you'll have like 2 of those circoms on one memory bus, and it's clocked at this speed. The memory bus is clocked at that speed, and there's a second memory bus that's separate, and then there's a big bridge that delegates from the CPU into those separate memory buses. What I found interesting is there's these 2 peri buses, but they can access the same peripherals, but not all of the same, like not all of the registers. So I thought this was pretty interesting, and it feels to me like something that you have to be very careful when you're using. So we just read this. It says, the CPU can access modules and peripherals more efficiently peripheral bus 1. Cool, great, right? Then through peripheral bus 2. However, peripheral bus 1 features speculative reads, which means it cannot guarantee that each read is valid. So it's fast, but it may not be correct. It says, therefore, the CPU has to use peripheral bus 2 to access some special registers, for example, FIFO registers. In addition, peripheral bus 1 will upset the order of read-write operations on the bus to improve performance, which may cause programs that have strict requirements on the read-write order to crash. In such cases, please add volatile before the program statement or use peripheral bus 2 instead. Yeah, interesting, right? So this is, you can access things more than one way. And actually, if we just keep scrolling down, these 1, 2, and 3s, I think are, you can access it from peripheral bus 1, you can access it from 2. But then 3 is like only some of the stuff you can only access from 1. Yeah. So I mean, it's interesting, right? Because you could actually you can actually choose which way you want to access things, because as we talked about earlier, right? The CPU is really quick, and the memory is slow, and it gets slower the further away you get. And so if you can be doing something on peripheral bus 1 and peripheral bus 2 at the same time, you can be faster. So this just seemed like a gotcha, like note to myself, like something strange is happening and not working. Like this is the thing that I would want to go back and check. Yeah, speculative reads. There was a bug that Damien was telling me about on the STM32H7s as well, because they speculatively fetch as well. And he had an issue where after like hours of running SSL stuff, he would end up hard locking, where like the debugger would die, like nothing would work again. And what he took him like a month, not because he's not smart, he's super smart, but because it's just so random. It was that as he was doing SSL computations, there was a value in 32 bits that looked like it was part of the flash, but it wasn't actually part of the flash. So it would try to speculatively read the flash outside the range of the actual flash and then just like hang because it wasn't valid. And so what he let me know, and I've learned from that, was that on the M7s at least, you have to be pretty particular about telling it like, oh, yeah, like your memory space is 8 megabytes, but the flash you're talking to is only 4. So like make sure that those other 4 are marked as invalid and not able to actually fetch. And this will probably, I don't know exactly where it is, but the ESP32, because it uses external memories, like that's another thing we still have to be aware of. Okay, so it's 3:30. I'll wrap up in the next 30 minutes. There's 2 other things I wanted to talk about. But Unexpected Maker has a question that says, but does CircuitPython have to work at such a low level? I get you want as much performance as possible, but with all the extra overhead of Python anyway, would optimizations at this low level really help? Yeah, that's a great question. And it's interesting because as CircuitPython went away from MicroPython, we explicitly said like, we don't care about performance. And here I am talking about performance. We said we don't care about performance, and that was really a shift to focus on usability. So we wanted to make sure we chose Pythonic APIs that may not be as performant, but would still be good, or that like we would choose Pythonic over performant. And I think the reason that we're starting to see a shift is that the IMX RT is really interesting. The bottom of the line is the IMX RT 1010, and it runs at 500 megahertz. And so if we're going to sell that, like the selling point of that is that it's fast. And so I started looking into this, not to eke out every last performance bit, but I knew that the other detail you need to know about IMX RT is that it doesn't have onboard flash. So all of the code and the data, the static data lives on the external flash. So it's kind of something we have to address if we're going to be able to say like we're using this chip in any sort of reasonable way. So I've only spent I spent a week on it doing like initial designations. The top of the line of the IMX RT does have onboard flash. I would be interested to see how fast the onboard flash is, because I bet it's still pretty slow. Um, but they have caches there as well. But like, my theory is that there's a lot of code that, so like the way the way that MicroPython and CircuitPython work is that there's this big loop, right? And this big loop is like, depending on the Python bytecode you're running, run a chunk of C code. And I think that means that as your Python code is running, it's churning through a lot of different C code. And so if you can manage to get that C code squirreled away close to the CPU, because you know you're going to be doing that loop, then you can free up any sort of caching resources that you have for all the dynamic stuff that you're loading, like the bytecode or the like C code for the individual modules that you've loaded in. So yeah, low-hanging fruit, as Unexpected Maker says. Yeah, it's more of a shift in mindset than a must optimize everything approach. Yeah, totally true. And it like the other thing is that CircuitPython as a separate project is maturing a lot. So like I spent the last month or two just like laying the foundation for us to do low power, which is also one of those things that 2 years ago we told people like it's not important to us. The reason that it started to become more important to us was because we were doing more Bluetooth stuff. So we wanted to have, I like did demos of like, oh, just set this thing on a battery. It broadcasts every 5 minutes. Like a sensor value, and the Raspberry Pi catches it. Like you start to see the things that would be enabled by doing low power. And I think that the same is true for performance stuff. So it's basically we don't want to have a really bad worst case. We want to do a decent job, even if it's not the best job. But we definitely won't sacrifice usability for it, for sure. Okay, so the other two things. The first is CMake. So CMake is an alternative to Make. Make people probably heard of Make. It's a super common system for deciding what files need to be compiled and then linked all together. And the way that MicroPython, and we've inherited this in CircuitPython, is that you basically have one giant make file that basically tells it all the different C files everywhere, and then they get compiled together and they get linked together, and that's kind of all that happens. But with the ESP32-S2, which is here, with the S2 support, they've switched to CMake from Make, I think. And CMake, I think, is, in my mind, having a bit of a renaissance from what I can tell. I was looking at it last night, and there's people don't like Make. I think one of the reasons people don't like Make is that it's really hard to have separate components of things. So, for example, like TinyUSB is a component that ideally, if you're using it, you can just say, I depend on TinyUSB, pull those files in, let them worry about what those files are. I'll just say I want TinyUSB. And that's not something Make can really do. So yeah, as Unexpected Maker says in YouTube, IDF 4.0 Plus in general is all CMake now, especially eventually phasing out Make. Professor Sparkle says, though I feel Meson is picking up now too. And I'm curious about that because I was looking at Meson as well. So I need to pick your brain. But the general Meson is interesting because it's Python based. The syntax of CMake is kind of weird, but it's also been around a while and it's supported by a lot of people. So this is why it's in my stew, my brain stew, because I'm not super happy with Make for CircuitPython. I have this longer term vision where we should be able to split off, like I showed it earlier, shared bindings. Like we should be able to split like common HAL out, right? Like we should be able to split the C level API for like SPI out into something else. We should be able to, in the same way that we split TinyUSB out into something, we should be able to do that. We should be able to split like the core Python mechanics that something is, I think Damien would love for us to share, is the like actual VM parts. Like we should be able to split that out from like other parts. And so the way that make just throws everything into a stew and like compiles it all and links it all it works. And Dan has done a number of refactorings to make it easier to configure, like when we include things for different boards. But it doesn't provide a lot of facilities for really doing much better build isolation. So I've been reading up on CMake because one thing, Espressif is choosing to go that direction, and they clearly know what they're doing. So I'm curious to see how they're doing it, and maybe we can dig into that just a little. And then, and yeah, it would be there's like two paths I can take for CircuitPython ESP32-S2 builds, right? Professor Sparkle says the running gag is that all CMake files are based on the first CMake file is very true. It's such an oddball language. Yeah, it looks weird to me, but there's lots of examples and documentation. In fact, one of the things I was reading is there's this modern CMake book that looks pretty nice. It reminds me of the documentation style of the Rust folks, which is also really good. So I'll drop that in the chat if folks want to take a look at it. So there are, since like what I found is like 2017, there was like a shift in how people use CMake, which I think I've run into it before then, but not looked at it kind of subsequently. So this modern CMake movement started with some talks at CPPCon 17, and there's been some really good kind of like best practices established after that. My other experience that's relevant to this is like I was at Google for 6 years. We used what has been released as Bazel, which is more Python inspired, sort of like define each thing individually and like bring in your dependencies that way. And they're like components and things, which is really good. It's all Java, which makes me not want to go that way. That's not interesting to me. But what you also see is if you follow this, people who were at Google like leave and go to like Facebook, and then they open source their build system that looks awfully similar to what Google had internally for a while. So it's quite nice. And so coming back from that to make is like, there's got to be something better. And Meson and CMake are kind of the two that I've looked at. And in fact, I found a bug. On Meson that was just somebody trying to use Meson to build the IDF with CMake. So it's something that people are doing, and that's interesting too. So if you have opinions about that, please let me know. Yeah, and the other thing that's weird about CMake and Meson, that's different from the way the make happens, is that it's actually like those systems, Meson and CMake, don't actually build anything. What they do is they generate files for like Make or Ninja that actually do the building. So building is more of a two-step process of you make a directory where you want it to end up, you run CMake, it dumps a bunch of files, and then you run the thing that actually does the build. Of course, you can like hide that behind one command, which is actually what idf.py does. So I'm curious to see like what the things that Espressif has layered on top of CMake as well, because I don't actually want to use that, right? Like CircuitPython is broader than the ESP IDF, so I'd like to use CMake or something CMake compatible, but also a system that works without the IDF, because like I'll prototype it for the ESP32-S2, but potentially later on we'll switch the other builds, other ports to that as well. So that's one thing in my brain. Are there questions about build systems? It's totally the weeds deep dive stuff for a Friday afternoon, but it's one of those things you got to think about. I don't see any. Unexpected Maker says CMake is so verbose, adding source includes for your source, so your source gets included. Yeah. The other thing I was seeing with CMake though is that tools like Clang Tidy are really, really handy. So people in CircuitPython, we've started to explore linters and formatters, and that's super. Uh, Drew Drew the Ogre says, if it's the weeds for a deep dive, wouldn't it be the seaweeds? Nice. And Joseph says, afternoon, lol. It's 0:44 a.m. here. Yeah. Cool. Awesome. I clarified something for Unexpected Maker. So we're helping each other out. They say I didn't realize it was a two-step process that makes so much more sense. Yeah, I didn't either. And it's kind of weird, but it's the right way to do. So that's why when you look at ESP IDF, they're CMake plus Ninja. Ninja is the thing that actually does the builds. And I looked at the Ninja page yesterday. I think it's Ninja build. Let's search. Yeah, ninjabuild.org. And it is interesting because it says it is designed to have its input files generated by a higher level build system. Right. And that's kind of the thing that people are finding. I think that's why make is weird for some people. So yeah. Make tries to be both, right? Make tries to be human readable and be quick about generating or building stuff. And Professor Sparkles also says that like Meson is the same way, which I'd love to. I want to chat. I'll chat with you more about Meson. Wait, I'll pull that up as well. Meson build system. So this is like something similar to CMake. Summersoft says make tries to be human readable. Lol. No, it's not that human readable, if at all. Especially some of the stuff that we do in MicroPython and CircuitPython. Yeah, so Meson is a project to create the best possible next generation build system. Depends on Python and Ninja. And it does the same sort of thing. So you change your source, you say set up your build directory, and then you move into the build directory and you type Ninja. So again, like it's a two-step process, not a one-step process. But I was already talking with Deshipu on the CircuitPython Discord, which you can go to at the URL adafru.it/discord. But he was like, could we just have a make command still? So yeah, we could totally have a make command, right? The make would just make the directory, run Meson, run Ninja, and you'd be fine. We got the pun masters in the chat today. Okay, so that's the other thing I'm thinking about. And so if you have experience on CMake and Meson, please, let's chat. One thing I've been thinking about, and one of the challenges that we have is CircuitPython is built for more than 100 boards now, which is awesome and cool. And if we just go to circuitpython.org/downloads, you'll see there's a lot of boards, and all these boards have slightly different configurations. And managing that is getting more and more complicated. If we could manage these in a way that was actually more similar across ports, that would be awesome. And I found CMake's notion of tool chains, which is how you can tell it like ESP32-S2 is Extensa, SAMD21 is ARM Cortex M0. Like we can do tool chains for that level, but it's not quite clear to me like where boards fit in that case. And so if you have an idea how that would work, I've been looking for like embedded uses of CMake to see if anybody's kind of figured out a best practice for it. And I've only found that like, oh, you should use tool chains to define like your ARM tool chain versus your Extensa tool chain. So I'll dig into the ESP32 IDF to see how they do that there as well. But I don't know. It's one of the things I got to stew on because my next steps are kind of like, okay, TinyUSB works. It was awesome, right? It just popped up. So I'll create a new directory, ports.esp32s2. If we pull up this, we can see that we have a ports directory. This is growing, which is awesome. We recently added LiteX, which is Python-based FPGA stuff, which is really cool. So we'll add an ESP32-S2 here. Then the question is what goes in it, and how do we hook it into ESP IDF? Because we definitely want to use the ESP IDF, and the reason that we want to use it is because the ESPs do networking, and networking is complicated. Networking and security is complicated, so we'd love to. We intend on hooking up directly to the IDF so that as they iterate, as they fix things, we just inherit it and we update the IDF. So that's why I'm like, okay, we can't really use make. Like we could use, so two options. We use our existing make system. We figure out everything in the IDF and its dependencies, what we need to include, and then we compile it all. But just saying that sounds like a bad idea because the other thing, the last thing that I want to just talk over, since this is just me talking, this is how my streams end up, is that because networking is complicated and Wi-Fi is complicated and you're scheduling stuff, they use FreeRTOS. FreeRTOS is a real-time operating system. That's what RTOS stands for. Yeah, Unexpected says, no, that's what MicroPython does. Please don't do that. We'll have to talk more. I don't understand the difference between the options there. But yeah, we'll talk more. We were talking earlier or yesterday as well. So if you have opinions about this, now's the time to explain things to me, which is why I'm doing this stream. So FreeRTOS is the other thing, the other piece of the puzzle that we have to think about, because there are a few cases of CircuitPython and of MicroPython being used within a real-time operating system. We've not done any of that with it, and Zephyr is the one that's been actively maintained from what I've seen. But it's not clear to me. I don't have a lot of experience with real-time operating systems. And the Zephyr in particular, I've looked into, and it's just this huge thing, and I'm not sure that I want to do that. I'm not sure I want to get into a giant ecosystem. Like they have their own build command and all this stuff, and I'd rather like stay away from anything super custom, which is why I don't really want to use like the ESP IDF like custom CMake commands. I'd rather not use those. I'd rather use stock CMake and then kind of bridge out to their custom stuff. Ian Pava asks Unexpected Maker, do you like the soft device binary blob kind of implementation for networking stuff like the NRF? I don't think that's directed at me, but I definitely don't. I do not like binary blobs at all. Yeah, so I mean, my hope would be that like we can attach ourselves to a particular version of the ESP IDF so that we can like say, oh, we're using 4.2, and then we like update to 4.3 and update to 4.4 and be deliberate about it. But I would like to keep us up to date with it. Binary blobs are just the worst because they're impossible to debug. When you don't have access to source code, you rely on the documentation that the people who do have the source code wrote. And that's just not always, it's oftentimes not adequate. Okay, so the other thing to think about is the way CircuitPython works right now, and this is another area that we've kind of split off from MicroPython. So if we pull up MicroPython, and we look in the root, there's no main. There's just markdown files. If you want to find main, it's actually different per port. So if you go here, ports STM32, there's going to be a main in here, main.c. And it's got all this stuff, file system mounting, reset modes, and all that. A while ago now, I factored that out in CircuitPython. So CircuitPython at the top level, we do actually have a main.c, and that main.c is used across all of our ports. And that was really important to me because main.c is the thing that does all of the highest level of management of workflow. And with CircuitPython, as we talked at the start of the stream before it crashed twice and blah, 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 is that the workflow should be identical across all of our ports. And the way to get the stuff to be identical that you want to be identical is to not have it port dependent. So we split out main, and then we introduced this idea of like a supervisor, and it's the supervisor API is the thing that like facilitates per port stuff that is kind of like needed in a standard way across different ports. One example is a serial connection. How does the REPL get and send characters? That is part of the supervisor API, and in fact, we actually have a common shared implementation of that uses TinyUSB under the hood, for example. So the question is how does FreeRTOS come into or interact with this highest level of our management? One thing we do that we're not super happy with, but it's still kind of working for us, is we do have this notion of background tasks, which is basically a function that we call as much as we can in between Python VM bytecodes. This is something like MicroPython does this as well, but we've kind of like separated it out a little bit differently. And that's where you'll get like, oh, you're playing an audio file and we have to buffer like so many samples. That will happen in the background. Another thing that happens in the background is like you wrote 512 bytes over USB and now we've got to flash it, and we have to like erase the flash and write the bytes and do the cache stuff. Like that happens in background task as well. And that's the sort of thing that an RTOS is good at managing, or at least should be good at managing. And we're going to need to sort out how that interacts with, we're going to need to sort out how CircuitPython interacts with another RTOS that's doing other stuff like that as well. I think what I was thinking is, I'll get to your question in just a sec. Unexpected Maker has a question. I think my answer is that I'm going to follow the TinyUSB model. Like Tack has a lot of experience, and he has this, if you notice in the name of the example is actually CDC mass storage free RTOS version. So TinyUSB already has a notion of an OS abstraction layer, and I don't know where it lives. It's somewhere in here. OSAL. So he's got an OSAL, and you can see that it has free RTOS and minute options in it, and then none. So when we use TinyUSB right now, we just do the none version. But we're going to get to this point where we are using free RTOS. And so I think what we'll probably do is inherit this OSAL from TinyUSB and use that as our way to like minimally plug into an RTOS, such as free RTOS that ESP32-IDF uses. So just to wrap that in a bow before I get to this last question, or one of the last questions, if you have more questions, please put them in the chat. We'll run through those and then we'll be done. But a call out, if you have experience with RTOSes, I'm looking for something minimal. I don't need HALs. I don't need like hardware APIs. I much prefer to just do register based if I can. But the scheduling and all that stuff is really interesting. So if you have experience with RTOSes, free RTOS in particular, let me know and help us out. Kind of refactor CircuitPython to be able to either run on its own or run in an RTOS. Okay, drop questions in chat if you have them, and I'll take this question from Unexpected Maker in YouTube. It says, side question, so what will happen for ESP32 only based peripherals like the RMT? Will you add stuff like that when it only works on one port? I don't know what RMT stands for, but we do have a policy for this, or an approach. So if it's a peripheral or a functionality that is doable on other ports, we'll add it to shared bindings and do that separation. if it's something really in the weeds of the port that is like very clearly port specific, the way that we handle that is we actually put that bindings and common HAL stuff within the port directory itself. You still need to make sure it's scoped on the module level, so that, as I talked about earlier, when you import, you find out whether you have it or not. But the way that we do it is we do it as a new module that's only available on a single port and is implemented within the ports directory. So Unexpected Maker says no OBS. It looks okay. That's bad. Let me pull up Restream.io. I'm so close. I'm so close to finishing. Let me see. Can anybody hear me? Or am I gone for everyone? All right, well, let me... yes, that's right. It's dropping frames. Okay, let me restart recording. This is great. Y'all are awesome. Hanging in with me. All right. I really appreciate everyone's resilience. All right, back on Twitch, back on YouTube. Let's take it home. All right. Bummer. Yeah, it was dropping frames as Unexpected Maker said. Okay, so I will just answer the question. This is the first time I've had problems with OBS. And the first two crashes I don't blame OBS for, really, since I was doing the thing. I will re-answer the question that I was in the middle of, since I don't know how far it got, although I got further in the recording. So the side question and the final question, because I haven't seen any more and you've had plenty of time, is what will happen for ESP only based peripherals like the RMT? Will you add stuff like that when it only works on one port? The answer is I'll probably not add it myself, unless that's useful. I don't know what RMT stands for. We'll talk about that later. But I can tell you what our approach is. So we do a similar split between the binding side, so the Python to C conversion, and then the common HAL stuff. We do that, but we do it in a way that is only in the ports directory. We don't put it outside the ports directory. We keep it in. And one example you can see that for is on this. If we just look in the Atmel ports, there's actually a common HAL here. And there's also this binding SAMD, where SAMD is a module and it has clock. It has a clock class that is like super specific to SAMD. That's a way that we can add port specific stuff if we need to. We do it at the module level. So if you import, it will raise an error if it's unable to import it early, which is really good. But if it's something more generic, like a certain functionality that is not port specific, but maybe only a few ports have, we'll still do it in share bindings and then just have some ports implement it. Okay, so yeah, that's how we handle it. It's doable. We want to be thoughtful about how we hook it in. So Ian asks, will this also be made available as a coprocessor approach, given it's cheaper than the ESP 32. Right. So the way that we do Wi-Fi now is by having a ESP32 as a coprocessor. Um, the question is, will we have the ESP32-S2 as a coprocessor as well? It's not our top priority. This is a good question and something I've been thinking about as well. Um, it depends on how hard it is. Like there's firmware on the coprocessor, and it depends on how hard it will be to migrate that firmware from the ESP32 to the ESP32S2. I haven't touched that firmware a lot, so I can't tell you how hard that might be. Um, I think native CircuitPython and Wi-Fi natively is definitely our priority, because having one chip is definitely always cheaper than having two. Um, but I have been thinking about, like, we've done a lot of work about MQTT, and Brent's been doing an awesome job adding support for like DHCP and DNS and stuff, all from Python. So I do want to take this as an opportunity to really refine our all our networking APIs. We have a lot of code written. Like we have a version of requests that we kind of maintain, and we have like socket implementations, but in particular, the socket implementations include APIs that are not actually on CPython socket, and that drives this spike through my brain a little bit. If I had my way, what would happen is that our shrunk down versions of big CPython libraries would be built on top of standard socket APIs so that we could test them in CPython on socket. The other thing that I've been thinking about, and this is all longer term stuff, right? Like the immediate term is getting to the point where we can get a CircuitPython drive and we can like import things and just do the workflow. Like that's the hardest part. And then you can add bus IO and all that stuff. That's easy once you get the workflow going. But I think like our other approach to networking has been a lot of native stuff, and I really want to reduce that. I want to minimize the amount of native stuff and make sure it's done at an API boundary that can be shared between the stuff that's done as a coprocessor as well. I don't want to end up having two worlds like we kind of have now. And then the other thing that informs that is thinking about lifetime. So the display IO work was a huge amount of work because I wanted the display to last longer than the user's Python code so that we could show errors and stuff on the screen. And there's this thing in MicroPython called the web REPL, where you can actually like go to a web page and do a socket and get your like serial input and output. And I don't think I want to do that. That will add complexity because it has that same problem of like its lifetime is different than the user's code. And I think with the networking stuff, both Ethernet and Wi-Fi, I'd rather move to a model where like the network stuff really only lives for as long as the user's code does, because that model means that we'll be able to do coprocessor stuff just fine. So yeah, we'll get there. That's further down the pike. We'll get the port set up, we'll get the RTOS and the CMake stuff sorted out, and then we can start refining the networking APIs. But okay, my voice is tired. I've crashed 3 times. So I'm gonna wrap it up. I will get. I hope to have all the recordings that I'll be able to like squish together and get on as one video. That will go up on youtube.com/Adafruit. I'll just do my standard spiel and get out of here. So this has been an Adafruit stream. I'm Scott. I'm paid by Adafruit to work on CircuitPython. We talked a lot about ESP32-S2 stuff today. And these are sporadic streams. They're deep dives. We also call them in the weeds. So if you have questions, you can always find me and a lot of other awesome people on the Adafruit Discord server. You can go to adafru.it/discord to hop in there. It's also discord.gg/Adafruit is another way to get in. We'd love to chat with you there. If you have experience with this stuff, please reach out. I'd love to get more people working on it than just me. Although this first bit of the workflow is really just like one person can do it because it's so the core of it. But yeah, if you'd like to support me and support Adafruit, you can go on digikey.com and buy Adafruit stuff right now. Adafruit themselves are not actually shipping anything except COVID-19 related stuff. Although you can buy IO Plus subscriptions to help us out and get some money coming in. And yeah, that I think is it. Thank you all for hanging in with me. The like actual coding and getting running part took like 5 minutes out of 2 hours. But crashes and installing things and things to thinking about all took some time. Kevin Walters asks, what's OBS? It's the Open Broadcast Studio. Anyway, it's Friday afternoon here in Seattle. Thank you all for watching, and keep an eye out for deep dives and a recording of this that is not 4 parts. Thanks all for hanging in with me, and we'll chat with you later.